All right, so our group did the heart pacemaker for our project, and it was done by me, Ian Bednarek, Rhys, Zach, and Antonio. All right, so the heart pacemaker in this model consists of a switch, which is labeled as S, a battery, a capacitor, which is labeled as C, and then it uses the heart as a resistor, which is labeled S on the model. And then whenever the switch S is at the point P, the capacitor charges. Whenever the switch is at the point Q, it discharges and sends an electrical stimulus to the heart. And then this diagram, E is the voltage, and the D value shows us the rate of change in voltage with respect to the time. All right, so to derive the equation from the model, basically this model consists of an RC circuit, a battery, and a switch. So we can use the generalized equation for the RLC circuits. From there, we can simplify this and rewrite it to remove the term with inductance. And after manipulating this, we are left with the given, which was provided in the instructions. And then down there's the equations that we got, which ends up resulting in d over dt is equal to -1 over RC times E. And to solve this generally, basically, you'd use the piecewise differential equation that was given to us, which is d over dt is equal to 0, or it equals 0 from between 0 and t1, whenever the time is at, and then it's equal to -e over RC whenever the time is between 1 and t plus. I'm actually bugging right now. All right. So then during the given time intervals, the switch is at the S, or is at the position P, which means that the capacitor is charging, but no voltage is applied yet. So since we know this, we only care about when dE over dt is equal to 0. And then we can solve this by using integration and cross multiplication. Then after doing that, the equation becomes that, which is the integral of d to 0 times dt to e equals k1 equals 0 times dt, the derivative of that, or I mean the integral. All right, so to further solve this, we can use the given conditions, which was e of 0 is equal to e of 6, which is also equal to e of 12, and e of 18, and all of these are equal to 0. So then since we said that k1 was equal to one of the e values, we can also derive that k1 is equal to 0. So then for those given time intervals, we know that e is equal to 0. And then on the opposite side, or the other hand, the given time intervals there, the switch is at the other position, which was q. And then for that, we only care about whenever d over dt is equal to -e over rc. And then we can solve that equation to get the equation down there, which eventually can become E equals e to the power of -t over rc plus c. Is that you, or do you want me to keep going?
Why don't you finish this point?
All right, I got you. All right, so to wrap up the solving it generally, we can further solve this equation by separating it into two pieces. So basically, you can set e to the power of c equal to c, and then the equation becomes big E equals e to the power of -t over rc times c. And then by using the initial condition e e to the t1 is equal to 12, we can use that to solve for c. And then yeah, there's the equation right there. And then eventually you can substitute c into the equation, where you solve for c and then substitute c into the initial equation, where you get 12 times e to the power of ti minus t over rc. And then since 12 was the value for e to the 0, the equation can also be written as e to the 0 times e to the power of ti minus t over rc.
Thanks, Ian.
Yes, sir.
This is Rhys, and now we're gonna go on to finally like looking at the full piecewise function and then solving numerically. So this slide just shows the time intervals for when the switch is at point P is discharge, right?
I
Well,
believe so.
when it's discharging, and then also the equation when it's charging so that there's no voltage through the heart. So in the instructions asked us to first model using Mach values for R and C, where it said R and C would be equal to 1. And as you can see, that's generally probably what we'd be looking for, something like a heartbeat. But obviously R and C don't appear to be correct numbers, as these this graph kind of cuts off oddly, where in a normal pacemaker we would expect the capacitor to fully discharge before switching back and charging again. So I did some research. It was generally kind of hard to find, but I found like very large range of values for which the resistance of a heart could be, almost certainly, because it would be very different for very different people. But the average adult would probably have a heart resistance somewhere between 800 and 900 ohms. And then the capacitance also appeared to be rather large, being somewhere between 40 to 100 microfarads. And for this model, because obviously there are so many values that could be, we're going to use like a very large range of, we're going to make several models at the extremities and around averages in order to try and get a more accurate model. So when we call an average equation, we're going to call it 60 microfarads and 1000 ohms. So obviously we solve for a range of values. So we're going to have a range of models. So first I highlighted the central one, which was the one that I would consider average, which is around 800 ohms and 60 microfarads. And yeah, it's basically just the model displayed. You see on the left for each one, there's the full map, which isn't very helpful. I don't think it's not easy to see a lot of the values, but then I also solved for a single pulse for all of them also. And as you can see, as the capacitance went up, there's more charge once the capacitor is fully charged, so it takes longer to discharge. And also for the resistor with more resistance, it also took longer to discharge. So yeah, you can see the progression. So the model appeared to work pretty well, and the capacitor would discharge at a decreasing rate, which we saw on all of these. And then and it would impart an electromotive force, which would allow the heart to beat. So yeah, these are our sources, and that's all we really have. You have anything else to add, Ian?
No, I think that's all.
Okay. All right. Thank you.
Thank you.